Hello everyone, I'm Wouter Tits and I'm working as an advanced development engineer at Powertrain, and I'm also the project lead for the ModulED project, which I'm going to present today. I will give a brief presentation, but I hope I will also give you the full view of the project. I will start with an introduction and give you a view on the consortium. Then I will go over to the project overview with objectives and the results. And I will finish with a demonstration and the project impact. The ModulED project is a European funded research project in the Horizon 2020 framework for the Research and Innovation Programme. We received the funding of the European Commission of 7.2 million euros, and the duration of the project was 3 years, and it was a little bit extended due to the COVID situation. The ModulED project aims at developing a new generation of modular electric powertrains for battery electric vehicles up to a full-scale demonstration integrated into a battery electric vehicle platform. The focus will lie on efficiency and cost in the hope to generate a massive adoption of electrified vehicles on the market. To do so, the consortium consists out of 9 European partners with different areas of expertise. First, we have CEA, which has also done the project coordination, and they have developed a GaN-based inverter. Secondly, Brusa company from Switzerland has done the development of the high-speed motor. Chalmers University from Sweden has implemented the regenerative braking strategy. IKA University from Aachen has done the system optimization, and Inextenso from France has done the life cycle analysis. Powertrain from Belgium was involved in the system design and integration, and Siemens assisted with the virtual performance. The University of Eindhoven has done the design for the multi-phase motor control, and ZG was in charge for the sizing of the transmission. During the project, the consortium has developed an innovative modular powertrain based on several new technologies. A battery electric vehicle can be charged from the grid, and the power will be converted and stored in the vehicle battery. The electrical power is passed to an inverter using wide bandgap gallium nitride semiconductor technology. This inverter will control the high-speed buried permanent magnet machine. The mechanical power is then delivered to the wheels by the use of a dual ratio high-speed transmission. An innovative regenerative braking strategy allows to maximize the recuperation of mechanical energy available during freewheeling and send it back to the battery. Next, an optimized cooling circuit will cool both the inverter and the motor. During the entire project, virtual modeling software and virtual assessment tools are provided and used to improve insights and results. Finally, a life cycle assessment is performed to map the sustainability of the final powertrain. To gain this broader acceptance of electrified vehicles on the market, a new generation has to be efficient, reliable, have a low carbon footprint, at a low cost, and needs to be compact and modular. Those prospects are defined as objectives for the ModulED project. To achieve these objectives, the project has focused on different technical areas, such as the multi-phase high-speed motor design with reduced rare earth magnets, a wide bandgap gallium nitride inverter with improved fault tolerance, a dual-speed transmission design, optimized thermal management system, improved regenerative braking strategy, and virtual assessment tools for sizing and optimizing. In the recent years, customer demand on electric cars is generating new challenges, mainly focusing on autonomy and on safety. This will depend upon the overall efficiency and the power density in the powertrains. To reduce the motor's active weight and to improve its efficiency, the main goal for the e-machine development was to save more than 50% magnet mass compared to existing permanent magnet synchronous machines with similar power. A buried permanent magnet machine was designed with a maximum speed of 23,000 RPM. This is, for example, twice the speed of the motor for the BMW i3. With a maximum torque of 160 Newton meters and a power of 150 kilowatts, the e-motor, in combination with the dual ratio transmission, can easily meet the end user's requirements. Further testing with higher currents has also shown that the e-machine has even a higher potential, up to 215 Newton meters and 220 kilowatts at 400 volt DC. You can see the motor performance in the picture on the left side. The graph also illustrates a good correlation between the measurements and the simulations. Thanks to the high-speed design, some advantages could be achieved. The uses of rare earth magnets could be drastically reduced compared to state-of-the-art. The magnet weight for lower speed E-machines of the same power is typically around 2 to 2.5 kilograms, while the ModulED motor is designed with only 1.35 kilograms of magnet material. The reduced magnet amount will also contribute to a favorable cost potential for the motor. With high-speed machines, it's possible to realize great power density improvements without compromising the motor efficiency or the peak power. Here, a volumetric power density of 26 kilowatt per liter is achieved. The high efficiency is possible due to the uses of an innovative formed Litzwire stator technology. The design contributes to the efficiency by reducing the copper losses in the system. The buried permanent machine is built with a 6-phase configuration. This increases the fault tolerance of the design and gives the motor a higher redundancy. The multi-phase machine also allows to operate with lower available currents and voltages, which is a good match for the GaN semiconductors on the market nowadays. The first motor developed uses sintered magnets, which will be glued or fixed in the rotor cavities. A second development is done in parallel, which used a new developed direct injection molding technology. Magnetic compound material is directly injected into the rotor cavities. The mold on the right is especially designed for the ModulED project. The rotor is clamped and maintained during injection, and at the same time, the magnetic compound is magnetically oriented by a 6-pole field generation with water-cooled coils. This method allows for almost full freedom in shapes. It can completely fill the cavities, and it offers a lower electrical conductivity. The main advantage is that the compound does not contain any heavy rare earth materials such as terbium or dysprosium, and also no gallium. Today, the technology is not yet standardized, and the cost per kilogram compound material is still higher with today's market prices due to the low production quantities of this compound. The rotor design is also specially adapted, and special shunts allowed for a more homogeneous field repartition. The residue, which you can see on the left picture, can be entirely recycled and reused. The magnetic field measurements in the graph on the right side show a good magnetic alignment of the compound and a perfect match with the simulations. In this overview, you can see the two motors that have been developed within the ModulED project, and you can see that they have almost the same performance. At the bottom, you can see that the magnet amount is reduced compared to the BMW i3 motor with about 52% for the sintered magnets and about 40% for the injected magnets. It is, however, to be noticed that the injected magnets do not contain any heavy rare earth material. Next to the E-motor comes the inverter. The inverter will transfer the power from the battery to the electric motor and controls it. The ModulED inverter is based on wide bandgap gallium nitride semiconductor technology. The GaN technology has unrivaled switching performance with switching times less than 10 nanoseconds. The switching losses are 13 times better than the conventional silicium semiconductors and 6 times better than the best silicon carbide technology. It has also very low conduction losses and no recovery losses. The small package allows for a high power density and provides good integration capabilities. The use of wide bandgap semiconductors will also increase the inverter efficiency. The ModulED inverter is powered by the battery and needs to supply the E-motor with 225 amps per phase to reach the requirement of 160 Newton meters. However, due to the lower current capability of the latest GaN switches, the maximal current per phase is limited to 120 amps RMS. This current corresponds to the continuous power of the electric machine. The used topology in the ModulED inverter is also not standard. The 6-phase full bridge independent configuration differs from the conventional configuration, where you would have a 3-phase half bridge with a star connection. This approach results in 12 independent connections between the electric motor and the inverter. An advantage is to increase the voltage per phase and to reduce the current per coil, which is necessary to reach the high torque demand despite the limited current capability. The used topology with full bridge configuration is expanded with a serial bidirectional switch or switches to allow to go from a 6-phase machine to a 3-phase machine. Each full bridge is therefore built by 6 gallium nitride semiconductors, resulting in a total of 36 devices for the entire inverter. The design is a modular setup with identical half-bridge PCBs, allowing for compact integration, and it also allows to isolate failures more easily to guarantee a better operational continuity. Additionally, the modularity can also decrease the service cost in case of failure. Switching from a 3-phase serial to a 6-phase parallel configuration could extend the full torque range to higher speeds. An increase in power becomes thus available. The 3-phase serial connection is, on the other hand, more interested at lower speeds by eliminating the additional switching losses from the parallel configuration. Changing between the serial and parallel control can be done dynamically, offering to work with a modulation of the signals. The losses can then be distributed as such over the several semiconductors, which will improve the thermal performance and also the lifetime of the devices. Using wide bandgap technology forces designers to reinvent integration architectures. The stray capacitance needs to be minimized and has to be decreased by a factor of 3 compared to conventional designs, leading to lower oscillations between the capacitor stages and lower reactive energy exchange, which improves the voltage stability across the GaN devices. The inverter currently has been tested up to 90 amps RMS, with a maximum efficiency reaches up to almost 99% at 25 kilowatts and 97% at 65 kilowatts. The main limitation seen here is directly linked to the thermal management of the small dies. This is why the requested torque cannot be reached. The losses are too high at high currents because the heat cannot be extracted out of the device efficiently enough. A better thermal conduction inside the die itself could overcome this limit in the future. Still, it has to be noticed that this is the world's first automotive inverter with such an output power. With high input speeds, also a high transmission is required, capable of making the needed reduction to the wheels. The implementation of 2 different ratios allows to select for an optimal operating condition. A concept generation tool is used to investigate the full range of suitable topologies. The best suitable is selected based on cost, size, and efficiency. The topology consists out of a Ravignon compound planetary gear set combined with a cylindrical final reduction. The 2 ratios can be established by either breaking the ring gear in first gear or in second gear, the second sun gear. The 2-step reductions lead to a high efficiency potential, which is realized with an improved gear geometry and improved bearing configuration. The full system deflections are included in the calculations, as well as the allowable production deviations of the parts themselves. Considering the high ratios of the high-speed transmission, the simulated efficiencies are good for both ratios, resulting in a 97.4% peak efficiency in first gear and a 96.7% peak efficiency in second gear. Additional attention was also paid to the losses from the auxiliary systems, which are continuously present. The low-loss passive lubrication system provides self-lubrication to all internal components without a need for an additional oil pump. To change between the 2 ratios, an efficient and low-cost actuation system is implemented. A torque interrupted shift is inherent to the design and will be investigated towards drivability. The design will only consume power during the gear shift and can therefore offer lower energy consumption while driving. All systems together are integrated in a very compact housing design. The inverter is fully integrated and positioned around the drive shafts, allowing for a higher power density and a lower cost. The powertrain with e-motor, power electronics, and gearbox with actuation system results in a full power density of above 3.25 kilowatts per liter. This is in line with state-of-the-art single-speed transmissions of the same power. Another integrated feature is the optimized cooling system. This optimization of the cooling system was done with the help of with CFD analysis. The cooling around the motor is designed in 7 parallel channels. The iterative sizing of the channels ensures a good and uniform cooling around the motor with a low pressure drop, as you can see in the graph on the right. Special attention is paid to the end winding by decreasing the thermal contact resistances and locally adapting the cooling design. Potting material is used to ensure a high heat rejection at the end windings. Also, the inverter cooling system is optimized to reject all waste heat and to maximize the current capacity as much as possible. The compact and power-dense GaN devices offer a big challenge to reject all waste heat. An integrated cooling block around the drive shaft cools all the half bridges uniformly to prevent temperature gradients between the gun devices. A geometric optimization of the pin-fin structure of the cooling plates results in a low pressure drop and a uniform flow field underneath the different switches. Commercial anisotropic thermal interface material with high in-plane conductivity was a perfect fit with the gun devices and resulted into a significant increase of heat rejection. At last, also the fluid distribution lines were investigated and optimized. A reduction in pressure drop of the distribution system to 1/3 was realized after the CFD analysis. Altogether, this results in a pressure drop of 260 millibars at 15 liters per minute, capable of rejecting the full waste heat of the powertrain. For the total cooling, a 30-watt automotive cooling pump would be sufficient. Regenerative braking allows to recuperate energy from the wheels back to the battery. An improved regenerative braking strategy is implemented to maximize the energy recuperation in balance with maintaining the vehicle stability. A conventional recuperation system has a constant front to rear brake proportion, which you can see by the red dotted line in the figure on the right. The ModulED strategy will be adapted towards real driving scenarios such as cornering. The recuperation is increased by maximizing between the ideal cornering curve and the maximal regeneration or ECE curve. The results give a significant gain in energy recuperation while maintaining drivability and safety. The conservative approach gives 7% increase, while an optimized strategy results in an 18% increase of regeneration. While high aggressive switch from accelerating to braking is performed, the driveshaft flexibility and the evaluation of the longitudinal acceleration of the vehicle clearly shows the need for a controller, which you can see on top. The powertrain controller suppresses the oscillations and assures a smooth torque transfer. The brake while cornering is evaluated, showing that the yaw rate and hence the maneuverability is increased with the ModulED strategy. Focusing on only the maximizing the regeneration would compromise the drivability. During the course of the project, support was provided by different virtual assessment tools. An holistic design approach was developed at the start. Based on the vehicle demands and the user requirements, possible concepts were generated. This includes e-machine design, inverter design, and transmission design. An interaction with different specialized software was done to improve the reliability. All separate designs are evaluated towards their individual requirements, and the designs that fulfilled the requirements were combined into all possible topologies, which were again evaluated towards the powertrain requirements and vehicle demands. From the system evaluation, several results and insights from interdependencies are presented to support decision-making in the project. A final powertrain concept could be derived eventually. The tool itself was still in development at the start of the project, and therefore the final ModulED powertrain concept was not yet a direct outcome of the tool itself. After the development of all parts and subsystem, the powertrain was assembled. Because of the torque limitation of the GAN inverter and the low maturity, a standard 3-phase inverter is used to conduct all tests. The powertrain is evaluated over the full functional range, and the project objectives of 23,000 RPM, 160 Newton meter, and 100 kilowatt are successfully achieved on the test benches at Punch Powertrain. The system evaluation on full system level shows a peak efficiency of more than 92% in first gear and 91.7% in second gear. Overall efficiency could have been even higher in case a GAN inverter was used. Next to the high peak efficiencies, the overall system also shows a large area with high efficiency, which will result in a lower energy consumption while driving. The combined efficiency maps demonstrate the improved system operating conditions while allowing more torque to the wheels and an increased top speed. By implementing a gear selection algorithm, the best gear is selected to meet the performance and to have the lowest energy consumption. The noise and vibration analysis is being performed to show that simulation model can be well correlated with the measurements. Here is also no expected behavior found. Unfortunately, the analysis is not yet completed today, and therefore an official statement has to be made in the coming weeks. Next to the powertrain assembly comes the integration in the demonstrator vehicle. The vehicle is assessed for energy consumption with different selection strategies. The maximal achieved energy recuperation is 234 watt-hours per kilometer. This does not include the charging losses. Note that the energy measurement is done without the GAN inverter. If it would have been used, the efficiency could be increased with up to 2%, especially at high speeds. The true potential of the powertrain is, however, not displayed with the WLTP cycle because of the general low torques and low power demand of the cycle. With heavier vehicles or more demanding drive cycles, the true potential of the dual ratio system could become visible. An expert drive is finally performed to assess the vehicle. The vehicle performed well to very well on drivability and has a satisfactory performance on MVH. We were also able to conceal the torque interrupted shifts and to guarantee comfort in most cases, thanks to an intelligent shifting control algorithm. In a few aggressive driving scenarios, on the other hand, the shift was inevitably present and further optimization is still possible there. Normally, we would be able to do a demonstration in real life, but unfortunately that is not possible. So I wanted to give you an experience through this video that we have made in the final phase of the project.
ModulED is a research project funded under the European Green Vehicles Initiative. It targets the next generation electric powertrains for full electric vehicles, focusing on high efficiency and low cost. The research in the ModulED project has produced a highly integrated and innovative electric powertrain that has been demonstrated in a vehicle. At the heart is a multi-phase E-motor based on buried permanent magnets that spins up to 23,000 RPM. This allows for a more compact design and a reduction of the use of rare earth materials. The E-motor is controlled by a GAN-based inverter using high switching frequency. This allows for lower losses and a very compact design. Its modular architecture reduces the service cost, and with multi-phase failure detection, the safety of the driver is guaranteed. Delivering the power to the wheels is the responsibility of a very efficient twin-speed transmission, containing an innovative topology, gear design, and bearing configuration. Its dual-speed arrangement allows the other components in the powertrain to also operate at their peak efficiency. Attention was also paid to improving the auxiliary systems, such as the actuation, cooling, and regenerative braking. A novel brake blending strategy maximizes the recuperation of energy while maintaining vehicle safety at all times. Built into the vehicle, all this research has resulted in a significantly improved range compared to the original powertrain. With the research, ModulED hopes to give a push towards mass adoption of electrified vehicles.
I hope this video gives a little bit an overview of the final stages of the project and gives a good demonstration of what we have done. So the project has investigated different research topics such as a high-speed motor, injection magnet motor technology, GAN inverter, high-speed dual ratio transmission, thermal management, regenerative braking strategy, and also virtual assessment tools. From a market point of view, the motor and transmission have a high maturity and technology readiness level and could be integrated on the market in the near future. However, the GAN inverter has still a lower technology readiness level and a high cost, further away from the market integration. The ModulED Consortium covers the full electric vehicle market. By providing low cost, efficient, and innovative technology, ModulED is addressing the need for the car manufacturers to be able to respect the CO2 emission regulations worldwide. On behalf of the consortium, I would like to thank you for your attention. My contact details and the project website can also be found at the bottom of the slides. Thank you.
Thank you very much, Wouter. Again, a very nice summary and a very lively and good overview on what has been achieved, what have been limitations also in the project, and what is also the room for future projects and future improvements. It's also good to know, okay, we are not at the end, so we can still improve, we can do further on top. There are a couple of very detailed questions in the chat. Maybe you and your colleague can answer. Maybe one quick vehicle speed. What is the vehicle speed maximum e-machine reached in first gear?
So we have 23,000 RPM e-motor speed. We have two ratios, about 21 and 12. So the top speed that we can reach is about 120, 130 kilometers an hour in first gear. In second gear, theoretically, we could go well above or above 200. In practice, it will be somewhere limited to 200.
Okay. But a quick question from my side, if you allow, the injected magnets are not using heavy rare earths, you're saying.
No.
Can you tell which material, which magnetic material you're using, or is this confidential?
It's not confidential. I don't know if Olivier is also in the call. He is more familiar with it. I know that it's a magnetic material compound, PPS based, to bind the materials, but the exact content of the magnetic material I don't know by heart. It's commercially available, at least from one company already. But maybe if Olivier is in the call, he can give a little bit more information.
Olivier, we have two Olivier in the audience, Olivier Charvet and Olivier Tosoni.
Tosoni, please.
Tosoni, okay, so let's grant panelist rights. And Olivier, you can take the floor, thank you. Okay, maybe.
There's another question on how polarity is identified in chat. So maybe Olivier or Wouter, you can answer in the chat so that we can move on. Sorry for this. So if you can please stop share screen and then